So thank you very much to the organisers for organising this very nice virtual conference and for the opportunity to speak. So I'm going to be talking about quasi-actions and almost normal subgroups. So to motivate the talk, I'm going to be talking about how quasi-actions arise quite naturally in various problems in geometric group theory when you want to study groups up to quasi-isometry. And I'm going to be talking about the class of Z by hyperbolic groups. Then I'm going to talk about the central notion in my talk, the notion of a discretizable space. And these are spaces which are coarsely discrete in the sense that every co-bounded quasi-action acts in a discrete way on the space. And once you have such an action, you have an almost normal subgroup, which is quite interesting. And then I'm going to talk about dichotomies between continuity and discreteness. So for instance, every finitely generated group is either coarsely continuous in some sense, which is the case if it's a co-compact lattice in a rank 1 Lie group, or when it's not such a lattice, it's coarsely discrete, it's discretizable. And then I'm going to talk about some applications to quasi-isometric rigidity. And in lots of situations, you have normal or almost normal subgroups being preserved by quasi-isometries. So a baby case that I'm going to be talking about is the following. It's the theorem of Kapovich, Kleiner and Lieb, and Moshe, Segev and White, or uses tools that they did. And it says the following: if we have a finitely generated group, quasi-isometric to a product of Z with a non-abelian free group, then the group is virtually Z times a non-abelian free group. So this class of groups is QI rigid. And in general, splitting as a direct product or even having an interesting infinite normal subgroup isn't a QI invariant. And this is illustrated most strikingly by the Berger-Moses groups, which are quasi-isometric to a product of two free groups, non-abelian free groups, but they're simple. So they don't split as direct products, they don't have any normal subgroups. And the broad outline of how you prove this theorem is the following. We have a mystery group G, and all we know about it is it's quasi-isometric to Z times F2. But we can show that it admits a weak sort of action, something called a quasi-action, which I'll define in a few slides, on F2, on one of the factors. And then a theorem of Moshe, Segev and White says that you can quasi-conjugate this, you can straighten this quasi-action to a nice isometric action. And once you do this, you can then look at the kernel of this action and show it's two-ended and then deduce the theorem. But these are the two key ingredients. And I'm going to be considering a more general class of groups, the class of Z by hyperbolic groups. So these are groups where you have an infinite cyclic normal subgroup such that the quotient is a non-elementary hyperbolic group. So it's a hyperbolic group which isn't finite and isn't two-ended. And I show the following, that every finitely generated group quasi-isometric to Z by hyperbolic group is also Z by hyperbolic. So this is a far-reaching generalization of the previous theorem. And to complement this, we have a QI classification. Two such groups are quasi-isometric if and only if their quotients are quasi-isometric. And the QI classification was actually known before, but the QI rigidity is new. And the key idea is, the first step of the proof is just as before, if we have a group quasi-isometric to a group of the form Z by Q, then the result of Kapovich, Kleiner and Lieb that I mentioned earlier says that G quasi-acts on Q. And this motivates the following problem. How do we understand quasi-actions of groups on more general hyperbolic metric spaces other than trees? And the point of the theorem, the point of this talk isn't just to prove this theorem, but is really to develop some machinery and some tools for understanding quasi-actions and some of the things that you can do with them. So what is a quasi-action? So if we have a group G and a metric space X, then a quasi-action of G on X, denoted by this symbol here, is a collection of quasi-symmetries of X, quasi-symmetries from X to itself, with uniform constants. So every Fg is a Ka quasi-symmetry for some uniform Kna, such that the following things hold. Firstly, if we apply Fh and then Fg, that's the same as applying Fgh up to some uniform error, and Fe, where E is the identity, is the same as the identity map up to some uniform error. And to simplify notation a bit, we'll write G.x rather than Fgx. And if we have two quasi-actions of G on X and Y, we say that they're quasi-conjugate if there's a quasi-symmetry from X to Y, which is equivariant with respect to these quasi-actions up to some uniform error. So if this inequality holds. And a key example is if we have a quasi-symmetry from X to Y, and we have an isometric action of G on X, then the quasi-symmetry F quasi-conjugates this isometric action to a quasi-action on Y. And part of the theory of quasi-actions is to do the other direction, to quasi-conjugate a quasi-action to a nice isometric action. So to motivate my approach to these things, I'm going to consider two hyperbolic groups which behave quite differently from the point of view of quasi-actions. So both pi1 of S is the fundamental group of a closed hyperbolic surface, and F2 is the free group of rank 2. And I'm going to claim that pi1 of S, from the point of view of quasi-actions, should be thought of as a continuous or smooth object, whereas the free group of rank 2 ought to be thought of as a discrete or combinatorial type object. And of course, both groups are discrete, so in some sense they're both finely generated groups, they both belong in the discrete world, but from the point of view of coarse geometry, pi1 of S should be on the left side because of the following theorem. This is due to Tukier, Gabay, Casson, Jungreis, and later refined by Markovic. And it says that every quasi-action on the fundamental group of a closed hyperbolic surface can be quasi-conjugated to a genuine isometric action on the hyperbolic plane. And in contrast, Moshe Zagiv White, I mentioned this result earlier, they show that every co-bounded quasi-action on F2, on the free group of rank 2, can be quasi-conjugated to an isometric action on a locally finite tree. And the point is that H2 is definitely a continuous smooth type object. You can take limits, you can do analysis on it, whereas trees are discrete combinatorial objects. They're locally finite graphs, so they belong on the right side. And some more qualitative differences between these two situations. So after we pass to the index 2 subgroup of orientation preserving isometries, the isometry group of H2 is a virtually connected Lie group. In contrast, the automorphism group of the tree with the usual compact open topology is totally disconnected. Similar situation, if we have the isometry group of H2 acts transitively on H2, the connected space, whereas the automorphism group of the tree has discrete orbits. So we'd like to say that pi1 of S is coarsely continuous in some sense, and F2 is coarsely discrete. And I want to make this precise and come up with a robust proper definition for what I mean by coarsely discrete, something where F2 should be coarsely discrete, but pi1 of S shouldn't be. And I want a lot more examples of coarsely discrete or coarsely continuous groups. And I want this to be useful. I want to be able to prove some interesting QI rigidity results using this technology, which I do. So here's the important definition. So I'm going to assume X is a proper geodesic metric space. And we say it's discretizable if it satisfies either of the following equivalent conditions. Firstly, every co-bounded quasi-action on X can be quasi-conjugated to an isometric action on a locally finite graph. And if you've seen other theorems where you quasi-conjugate quasi-actions to isometric actions, you might feel a bit disappointed by this because X might be a nice space with interesting local geometry. It might be a symmetric space. It might be a building. It might be a nice cat-zero cube complex. And we ruin all of that local geometry by passing to Y, which is just some locally finite graph quasi-isometric to X. The key point is not the geometry of Y, but what you can deduce about G and how it acts on Y, knowing that you have an isometric action on a locally finite graph. And this motivates the following equivalent formulation. Any co-bounded quasi-action on X has something called a coarse stabilizer. So what's a coarse stabilizer? If we have a quasi-action of G on X, we say some subset of G is bounded if a quasi-orbit is bounded. And if one quasi-orbit is bounded, then every quasi-orbit is bounded. And then if we have a subgroup of G, we say it's a coarse stabilizer of the quasi-action if, firstly, it's bounded, and then every bounded subset is contained in finitely many left H cosets. And the first condition, the H being bounded, vaguely says that H can't be too big, and the second condition says H can't be too small. It has to be just the right size to capture enough of the geometry of this quasi-action. And a key example is that if we have an isometric action on the locally finite graph, then the stabilizer of a vertex is going to be a coarse stabilizer of this action. And so this, in the definition of discretizable spaces, this gives the one implies two direction. And it's not hard to show two implies one. But going forwards, having a coarse stabilizer is really the property that we want, the property we want to use, and tells us about the structure of G. So this is really the definition that we want. And this is closely related to the notion of an almost normal subgroup. So we say that a subgroup of a group is almost normal, denoted by this squiggly triangle symbol, if every conjugate of H is commensurable to H. So, for example, every normal subgroup is almost normal. But additionally, here's an example of a group which contains a almost normal subgroup that's not normal. So we have the Baumstad-Solitar group, BS12. That's the group given by this presentation here. And the infinite cyclic subgroup generated by A is an almost normal subgroup that isn't normal and isn't even virtually normal. And more general example, if we have a group acting on some locally finite graph, then the stabilizer of a vertex is an almost normal subgroup of the group G. So these are quite ubiquitous, and we can already see the connection between almost normal subgroups and discretizable spaces. And there's also a notion of a quotient space. So if we have a normal subgroup, then we have a quotient group. If we have an almost normal subgroup, we have a quotient space. So a space which is well defined up to quasi-isometry and essentially has all the geometry you'd expect the quotient group to have, except it may not actually be a group. So we say that a group is finitely generated relative to a subgroup if there's some finite set, we can assume it's symmetric, such that that set union the subgroup generates the whole group. And the quotient space, if we have an almost normal subgroup of G, then the quotient space as a set is the set of left cosets, and it's equipped with the relative word metric. So the distance between two cosets, GH and KH, is the least n such that G inverse K can be written in this form. And it's not hard to see that this quotient space is a proper quasi-geodesic space. So it's quasi-isometric to a geodesic metric space. It's discrete, and it's well defined up to quasi-isometry. So it doesn't matter what finite relative generating set we pick. This is a well-defined space. And going back to our example on the previous slide, if we have the Bam-Flux volatile group and the infinite cyclic almost normal subgroup H, then the associated quotient space is just quasi-isometric to the Basset tree. And one of the nice things about discretizable quasi-actions, discretizable spaces, is that if we have a co-bounded quasi-action on X with a coarse stabilizer H, then we have the following analog of the Milnor-Schwarz lemma. So the group G is finally generated relative to this subgroup H. H is an almost normal subgroup of G, and the quasi-action of G on X is quasi-conjugate to the isometric action of G on the quotient space. So essentially, once we know we have a coarse stabilizer H, we can forget about the original quasi-action, and all of the geometry of that quasi-action up to quasi-conjugacy can just be seen from the isometric action of G on its quotient space. So it acts just by normal left multiplication of cosets, and we've replaced this not nice quasi-action with a very nice algebraic concrete isometric action. And so an interesting corollary of this is that if we have two co-bounded quasi-actions, G on X and G on Y, and they have coarse stabilizers H and K, then the two quasi-actions are quasi-conjugate precisely when H is commensurable to K. So this geometric problem of deciding whether two quasi-actions are quasi-conjugate is actually can be converted into an algebraic problem, just deciding whether these subgroups are commensurable. And another observation is that if the group is finitely generated, so that means the group itself has a nice geometry, and we have an almost normal subgroup, then the group can be thought of as the total space of a coarse bundle over the quotient space, where fibers correspond to left H cosets. So I'm not going to define what a coarse bundle is, but the intuitive idea of it is this picture here. So what happens is this is the Cayley graph or Cayley complex of the Bam-Flux volatile group. And if we collapse all the left H cosets to points, we sort of get this, we get the Basset tree of the Bam-Flux volatile group. And likewise, if we take 3 images of points of the Basset tree, we recover the original group. And this sort of coarse bundle stuff, this coarse bundle terminology has been used in lots of important QI rigidity results, for instance, by Faber-Moshe, by White, by Moshe-Segev-White, and Eskin-Fisher and White. And it's an important tool. And just having this almost normal subgroup gives you this structure. So far, the only discretizable space, coarsely discrete space that we've encountered is the free group, but actually there are loads of them. It's a very ubiquitous concept. So we have the following trichotomy for top hyperbolic spaces. So the continuous case, here every co-bounded quasi-action is quasi-conjugated to an isometric action on a negatively curved homogeneous space. So these negatively curved homogeneous space have Lie group, have group of isometry as a Lie group, and they're virtually connected in most cases. So we have, this is the coarsely continuous case. Then there's a mixed case, which is action on a space which has both discrete and continuous behavior. So every co-bounded quasi-action can be quasi-conjugated to an isometric action on a pure Milfaux space. So these were defined by Capras, Cornulier, Monod, and Tessera in their study of locally compact amenable hyperbolic groups. And these are sort of a warped product between a tree and a negatively curved homogeneous space. And so the discrete behavior comes from the action on the tree, and the continuous behavior comes from the action on the homogeneous space. And if we don't have one of these special cases, then the group X has to be, space X has to be discretizable. So that means every co-bounded quasi-action on such a space can be quasi-conjugated to an isometric action on a locally finite graph, or equivalently, we have a coarse stabilizer. So this situation arises very often. And if we're only interested in from of hyperbolic spaces, quasi-isometric to finitely generated groups, then we can be a bit more specific. Then in the continuous case, every co-bounded quasi-action is quasi-conjugate to an isometric action on the rank 1 symmetric space. So this is a lot more structured than just knowing a negatively curved homogeneous space. And the discrete case, if we're not one of these things, every such space is discretizable. So in particular, using the QI rigidity of co-compact lattices in rank 1 Lie groups, we can deduce that every hyperbolic group is either virtually a co-compact lattice in a rank 1 Lie group, or it's discretizable. And this is the key point. And I'm not going to prove this theorem, but I'm going to indicate some of the key steps in doing this. So using the geometry of this quasi-action, we give G the structure of a topological group. This is based on work of Kevin White. And this topological group a priori won't be locally compact. It may not even be Hausdorff, but you can quotient out by something to make it Hausdorff, and then you can then complete it to a locally compact group. And this is all done by Kevin White, essentially. And then once we have a nice locally compact group, we apply some structure theory due to Montgomery-Zippin and Gleason-Yamabe in their solution to Hilbert's fifth problem. And we essentially deduce that it's a Lie group or it's discretizable. It may be the case, there's another case to consider, which is when this locally compact group G hat is amenable. So for instance, the action of the Bamslag-Solitar group, BS12, on the Basset tree, when we complete that, we get a locally compact amenable group, and in which case the work of Capras, Cornulia, Monod, and Tessera that I mentioned on the previous slide classifies all of these groups, or characterizes all of these groups. And this phenomenon isn't just something that happens in negative curvature or coarse negative curvature, but it holds much more generally. So for instance, the group of virtual cohomological dimension 2, which is finally presented, then one of the following holds. Either it's virtually a surface, so virtually z squared, or virtually pi1 of a compact hyperbolic surface, closed hyperbolic surface. The mixed case, in which case it's a generalized Bamslag-Solitar group. And so these are groups which are sort of coarsely warped products of a real line and a tree. And again, like Milford spaces, we have the continuous behavior coming from the action on the real line and the discrete behavior coming from the action on the tree. So these groups exhibit a mixture of coarsely continuous and coarsely discrete behavior. And everything else is discretizable. And this uses very different methods. It uses the structure of the second cohomology and ideas due to Farrell and Kleiner, as well as a bit of JSJ theory. I'm not going to be talking about this case anymore. And I'm going to be going back to my original theorem that I stated near the beginning of the talk. If we have a finitely generated group quasi-isometric to a Z by a hyperbolic group, then it has to be Z by a hyperbolic. And we now have the tools to prove this. So firstly, if a group is Z by a hyperbolic, then it's virtually central. That's very easy to see. And then the result of Gersten says that it has to be quasi-isometric to a product of Z times Q, where Q is the non-elementary hyperbolic quotient. And this uses the fact that the comparison map from bounded cohomology to ordinary cohomology in degree 2 is surjective. So the cocycle defining the central extension is a bounded cocycle. Then the result of Kapowicz, Kleiner, and Lieb that I mentioned at the beginning says that if we have G prime, which is quasi-isometric to G, then G prime has to quasi-act on the hyperbolic space Q. And now there are two cases. So Kleiner and Lieb prove the case where Q is quasi-isometric to a rank 1 symmetric space. And they use the fact that you can quasi-conjugate the quasi-action of G prime on Q to an isometric action on the symmetric space. But even then, you're not done, because you have to show that modulo the kernel of the action, that this is a proper action. And you can do this, but it involves growth estimates. It's not immediate from the QI classification of quasi-actions on rank 1 symmetric spaces. However, if the space Q isn't quasi-isometric to a rank 1 symmetric space, then it has to be discretizable. And then we're basically done, because we have a coarse stabilizer H, and it's not hard to see that the coarse stabilizer has to be a two-ended group. And without loss of generality, we can assume it's actually infinite cyclic. And we have an infinite cyclic almost normal subgroup. And so there's a homomorphism from the total group G prime to the abstract commensurator of H, which is isomorphic to Q. And this is sort of an analog of the fact that if you have a normal subgroup, then you have a homomorphism to the automorphism group of the normal subgroup. Here we only have an almost normal subgroup, so we have a homomorphism from the ambient group to the abstract commensurator of the almost normal subgroup. But because H is undistorted, because it's quasi-isometric to Z times NQ, and H is finite Hausdorff distance from the sort of Z factor in this direct product, the image of this map phi has to be contained in 1 minus 1. And that means you can pass to some finite index subgroup of H such that G prime normalizes that subgroup. And now we're done. So an interesting observation that we make here is that actually the discretizable case, where we don't understand as well as the rank 1 symmetric space, is actually much easier. So this is a sort of paradoxical little fact that it's much easier in the generic case, any hyperbolic group that's not quasi-isometric to a rank 1 symmetric space, which are essentially the prototypical hyperbolic groups. So in some sense, the prototypical hyperbolic groups aren't very representative of the whole family of finely generated hyperbolic groups. And we can generalize this, or partially generalize this, to other central extensions. So if we assume that we have a residually finite group, which is quasi-isometric to a central extension of Zn by Q, where Q is a non-elementary hyperbolic group, then G has to be a central extension of Zn by Q prime, where Q is quasi-isometric to Q prime. And one thing that jumps out at you is I assume the residually finiteness. Do I need to? Why? What's going on here? How is it relevant? And this uses subgroup separability in some way, and the observation that if we have an almost normal subgroup, which is separable, then that's a sufficient condition for the group to be commensurable to a normal subgroup. And that's what you want to do to prove this. And if we don't assume residually finite, then we can still deduce some interesting algebraic information. So if we have a group G, which is quasi-isometric to such a central extension, then there's an almost normal free abelian subgroup such that the quotient space is quasi-isometric to Q. And moreover, because it's quasi-isometric to a central extension, we see that the natural map from G to the abstract commensurator of Z to the N, which is isomorphic to GLA and Q, is actually contained in the group of orthogonal n by n matrices. And this sort of indicates why things are easier when n is equal to 1, because orthogonal 1-by-1 matrices are just 1 and minus 1. But when we have z squared and z cubed and so on, we have sort of more room to move around without distorting distances. And recently, Leary and Monestian gave examples of cat-0 groups that aren't biautomatic. So these are groups which, in particular, these groups are quasi-isometric to z squared times f2, but they have no normal z squared subgroup. So these are sort of counterexamples to the theorem at the top of the slide if we remove the residually finite hypothesis. And if you read their paper, you'll see that these groups are H in an extension defined by some orthogonal matrix. So you'll sort of see this map to the group of orthogonal matrices in their paper. So some future directions that I could take this research and what applications is for something, a question I've been thinking about a lot, is for which finitely generated groups G and normal or almost normal subgroups H is the following sort of meta theorem true. So do we have, if we have some finitely generated group G prime, which is quasi-isometric to G, then there's some normal or almost normal subgroup H prime, which is quasi-isometric to H, such that the associated quotient groups or quotient spaces are quasi-isometric. And in general, there are lots of counterexamples to this thing, but there are also lots of interesting cases where it is true. So known cases include if we have a central free abelian group and the quotient group is Qi to a symmetric space of non-compact type. Several instances where both the normal subgroup and the quotient are free abelian. So in the nilpotent case, this is due to Gromov. In the non-nilpotent polycyclic cases, this is due to Eskin, Fisher, and White, Peng, and Demars. If H is an almost normal subgroup of G and the quotient space is quasi-isometric to a tree, then that was shown by Moshe, Segev, and White. And this is actually equivalent to G being a graph of coarse Poincare duality groups. And more generally, if we have an almost normal coarse Poincare duality group such that the quotient space is infinite-ended, and we need to assume a few very mild fineness hypotheses, then in this situation, we also have a positive answer to the meta theorem. And if we have central z to the n, such that the quotient is hyperbolic, then it's also true. And that's what I've been talking about in this talk. And there are many more cases and many more applications for some of the machinery. And the ideas and concept I talked about shows that demonstrated this question could hold in a lot more cases. We could have Qi invariants of normal subgroups much more often than was previously thought. Thanks very much for making it to the end, and please get in touch if you have any questions or comments. Thank you very much.